Okay, so in this lesson, we're going to think about finding the CDF for a discrete random variable. And we don't necessarily need to do this because, as we've been talking about discrete random variables, we can use the PMF to find probabilities. We don't have to use the CDF the way we have to for continuous random variables, but it's kind of easier to see what's going on if we work with a discrete random variable first. And so what I've done here is I've illustrated a PMF for the kind of ad hoc, made up, for example, discrete random variable that we've been working with really for many weeks now. So more typically, the way we might write this PMF would be in a table. We haven't usually been graphing them. What we would normally do is just say, well, X can take values 1, 2, and 3. Okay, so those are the values. And the probability that X takes each of those values, well, the probability that X takes the value 1, that's 1/8, and we're just reading it off the height of the PMF there. That's 1/8. And the probability that X equals 2 is 1/4. Fine, it's 1/4. And the probability that X equals 3 is 5/8. Good. Those probabilities sum to 1, so it's a fine PMF. And then if we wanted to derive the CDF for that, just to remind ourselves that what is the CDF? That capital F of X, the CDF of X evaluated at B, is just the probability that random variable X is less than or equal to B. And how do we get that? We sum up the values that X can take that are less than or equal to B. We sum up their probabilities. Okay. So doing that in the context of this particular random variable, let's extend things here to make a column for the CDF. Okay, so first I'll just stick with kind of the values that we assign probability mass to. So the probability that X is less than or equal to 1, okay, well, less than or equal to 1, it's not going to be less than 1, okay, but it's going to be equal to 1 with probability 1/8. Now we want the probability that X is less than or equal to 2. Well, it could be 1 or 2, and that would be 3/8. Okay. And then what's the probability that it is less than or equal to 3? Well, it could be 1 with probability 1/8, 2 with probability 1/4, or 3 with probability 5/8, and that would be 1. Okay, and that's exactly what's going on in this picture here. What I didn't write in the table, and again seems kind of unnecessary with a discrete random variable, although it's certainly not wrong, is that the probability that X is less than or equal to B is 0 as long as B is less than 0. Okay, so we might even, if we're being careful, write that in here. I'll do it in a different color. F of X equals 0. Let me write my B in there. 0 for B strictly less than 1. Okay, so as long as we have a value of B that is less than 1 the cumulative probability. The probability that's less than b is 0. And then right at 1, I've got a place where there's like a open dot at 1 because the function jumps. Now, once b becomes 1, now the probability is 1/8. Okay, and it actually stays at 1/8 right up until we get to 2, and then at 2, again, it jumps here, jumps to 3/8, because now it can either take the value 1 or the value 2, and both of those are less than or equal to 2. Okay, and then then it stays at 3/8 here, going along for all these values between 2 and 3. And then when we get to 3, all of a sudden the probability that x is less than or equal to 3 is 1, because yes, x is always less than or equal to 3. Okay. So as I say, you wouldn't need to do this. The calculating the CDF is kind of an unnecessary step here when we can actually assign probabilities to the individual events, but the logic is the same, and it's to some extent, I think, easier to see here. You also see some of the features that I mentioned in the last lesson of CDFs, that they're always kind of like weakly increasing. So these are flat for a while, but the point is they never go down, and that eventually the CDF becomes 1. Okay, so fine. Next lesson, we'll do CDF for a continuous random variable, where we really do need to have that CDF to calculate probabilities. The CDF is the function that assigns probabilities to continuous random variables, and it assigns probabilities to intervals, not to individual values. So I'll see you in the next lesson for that.